I wanted to show you one of my favourite props from last year's Christmas lectures, which is a Mobius strip steel track covered in maybe 2,000 or 3,000 of these super strong neodymium magnets. So what I want to show you is how this track is going to interact with one of these. This is a high temperature superconductor made of yttrium barium copper oxide. It's a sort of ceramic material. And a superconductor is something that when you cool it down, in this case with liquid nitrogen, loses all its electrical resistance. So this leads to some interesting behaviours, which I'm going to show you. And to do that, I'm going to need to hang this thing from the ceiling, which I'll do now. Oh. So we have one suspended, super strong, neodymium magnetic Mobius strip track. All we need now is some liquid nitrogen. So we're down in one of the labs at the RI. This is where the liquid nitrogen is stored. Right, that'll probably do. Superconductor is now cooling down, which will take a minute or so. It needs to be cooled down in situ because what I'm trying to get to is to have the superconductor kind of locked into this position. So I need to cool it down in situ above the track. I'm cooling it down past its critical temperature, the temperature at which it will become a superconductor and its electrical resistance will completely disappear, which is about minus 180 degrees. The burger tray is there, maintain a spacing between the superconductor and the track. I mentioned that we're trying to lock it into a specific position, so that is the position that we want it to take up. Just going to slide this off. This is the best way I've found of doing this. If I hold this up quickly enough, you can see there that it's actually levitating on the track. You might be able to see a gap underneath it there, sliding back and forth, levitating. Oh, and okay, there. So unfortunately, it warms up quite quickly because obviously the effect only works as long as it's at its superconducting temperature. So what's actually going on there? A good way to start to understand that is to think about how magnets interact with ordinary conductors like this copper tube. So if I just drop this nut through, it falls all the way through very quickly, as you'd expect. If I drop a strong magnet through instead, it takes quite a long time. And the reason that's happening is as the magnet moves through the copper, it induces electric currents in the copper. Those electric currents themselves have their own magnetic field, and that magnetic field will always arrange itself so as to resist the motion that's creating it. And this is the fundamental principle of electromagnetism, that moving magnets near conductors or moving conductors near magnets creates electric currents. Now, because this is not a superconductor, because it has electrical resistance, the currents that are created as the magnet falls through will always tend to die away. So if the magnet were, for instance, to be stopped by the electric currents, those currents would immediately die away and the magnet would start falling again. So what actually happens is it just falls slowly through the tube. If, however, this were a superconductor, those currents would not die away. As soon as you induce them by introducing the magnets into the tube, those currents would remain and would keep going even after the magnet has stopped. So if this were a superconductor, the magnets would basically be locked in the pipe. They would be effectively levitating in the pipe indefinitely. So that's part of the explanation. We're sort of halfway there. I'm going to get onto the track now. And to do that, we saw when I was demonstrating the superconductor on the track down here that the effect only lasted a few seconds. It warmed up too quickly. It warmed above its critical temperature and stopped levitating. The solution we decided on for the Christmas lectures last year was to make a little train/boat thing. So we've got a piece of the superconductor embedded in polystyrene with its own little reservoir for liquid nitrogen. So let's cool this down. Again, I'm going to, not a burger tray this time, a slightly different dish. Carefully pick it up, and I think, so now I can send it round, come all the way back, go back on top. This is why we made it like a Mobius strip, so it can go, so it comes back from the opposite side it went round. So if I just stop it there, so it's kind of locked into position. So it's not just repelling the magnets and hovering. I can sort of pick it up and then stick it underneath as well, and it will hang there. So as I mentioned with the copper, when you induce electric currents in conductors with a moving magnetic field or changing magnetic flux, the electric currents that you create will always have their own magnetic field that resists that change, that resists that motion. So when it's hovering on top of here, and gravity is trying to pull it towards the track, that small motion towards sets up electric currents in the superconductor which have a magnetic field that resists that motion. But likewise, when it comes around and it's now on the other side, now gravity is trying to pull it away, so that act of trying to fall away from the track sets up a different set of currents with a different magnetic field, which this time attract it to the track. So whichever way you try and move it, whether you're trying to move it off to the side, up and down towards the track, away from the track, the superconductor will resist that motion, effectively locking itself into position relative to the track, so that the only direction it can move is the direction in which the magnetic field doesn't change, i.e. along the track. So basically, the superconductor can be any kind of magnet it wants to be, or any kind of magnet it needs to be at that moment to keep itself in the right position relative to the track. So this material was a real breakthrough, and possibly the first step on the way to what might be the holy grail of superconductor research, which would be a superconductor that would operate at room temperature or close to room temperature, at which point we might be able to use them to replace all of the conventional conductors like copper and things that we use in all our electrical applications today. And all of those materials, when they conduct electricity, they do it inefficiently to some extent and waste energy. If we could superconduct in those applications, then that would really change the world.